All right, so let's take a look at the answer key to this balancing equations practice worksheet number 2. Keep in mind that balancing means that you have the same amount of products as you have reactants. Reactants are on this side. That's what you start with. Products are on this side. That's what you finish with. So we have to count the atoms on the reactant side, our ingredient side, and then make sure we have that amount on the product side, because you can't make the products if you don't have enough reactants. So let's see here. We've got 1 sodium here and 2 sodiums here. That's unequal. So I need to make this 2 sodiums on this side. Remember that the only numbers that you can change are the big numbers, what we call the coefficients. So I can put a 2 in front of that and say now that I have 2 sodium chlorides, which would give me 2 sodiums, which is what I need to make this product over here. So now the sodiums are balanced. Well, that also means I have 2 chlorines. If I come over to the product side, you can see I only have 1 chlorine over here, and I can't put a 2 down there because remember that number comes from the cross and drop. I can't change the subscripts. I can only change the coefficients. So if I put a 2 here that gave me 2 chlorines on the reactant side, I can put a 2 over here that gives me 2 chlorines on the product side. Now I've got 2 sodiums and 2 sodiums. 2 chlorines, 2 chlorines. Now this also gave me 2 hydrogens. If I come back to this side, I can see I have 2 hydrogens, so those are balanced. I have 1 sulfur, 4 oxygens, 4 oxygens. This one is now balanced. So in terms of what type of reaction this is, well, here I've got a compound and another compound. And we see what's happened over here is basically the sodium took the place of the hydrogen took the place of the sodium. They switched places, or they replaced each other in the compound. I started with 2 compounds and I finished with 2 compounds. This is what we call a double replacement or a double displacement. You'll see both terms because we had 2 compounds that both had something replaced in them. 2 things that were switched, so this is called a double replacement. Now, I'm not going to work through each one of these as lengthily as I did this one. So this one was I'm about 2 minutes into this, and we've got a lot of equations. So what I'm going to just do now is show you the answer key from this point on. And if you have questions about where a number comes from, or if I think it's going to be a little confusing, I will pause the presentation and I will actually interject that to the video. This one here, I actually don't have to do anything to, because if I look, I have 1 zinc and 1 zinc. This is 2 oxygens, and I've got 2 oxygens on that side. I've got 2 hydrogens and 2 hydrogens, so it was already balanced. This is a decomposition reaction because you start off with a compound and you break it apart. You decompose it into 2 separate components. Synthesis reaction because you have 2 things being added together to synthesize or form a new compound. All right, so this type of reaction is called single replacement because I have a single element and a compound, and I finish with a compound and a single element, and we had 1 thing replaced in this compound, so it is a single replacement. So here's my coefficients that makes this one balanced. See, we have 2 compounds and they were both switched. So that is a double replacement. I'm going to start using the abbreviation DR to represent double replacement, SR for single replacement. I'll use S for synthesis and just the letter D for decomposition. Here's my coefficients that makes it balanced, and this would be a single replacement. Here's my coefficients that makes everything balanced. This is a decomposition because we have a compound. We have 2 elements that are stuck together, and then we decompose them. We break them apart into their individual elements. So here's my coefficients that make this balance. So I'll have 2 potassiums, 2 potassiums, 2 bromines, 2 bromines, 1 lead, 1 lead. Got 1 of these SO3 things on both sides, so it's balanced. This is a double replacement because we have two compounds that are both being switched. Double replacement. Now this one's already balanced because we see we have one sodium and one sodium. One carbon, one carbon. Now I've got two hydrogens on this side, and over here the two hydrogens are together, but I have two on this side and two on this side. Three oxygens over here. So I have two there plus another one there. That makes three oxygens. This equation was already balanced as written, and this would classify as a decomposition because it has more pieces when it's done than when it started. So we had two things and broke them apart into three. All right, now this one here is called a combustion reaction because we're combining something with oxygen, pure oxygen, which is what we know a fire needs. And your products are carbon dioxide and water. That's the definition of a combustion reaction. Let's count up the atoms here. We've got 4 carbons here, 4 carbons there. It's balanced. Now on this side, I got 2 times 6 hydrogens makes 12. I'll take 6 times 2 on this side makes 12. They're balanced. Let's look at the oxygens now, though. We've got 4 times 2 there makes 8 oxygens. But 6 times 2 here makes 12 oxygens for a total of 14 oxygens, which is why I put a coefficient of 7 here, because 7 times 2 makes 14. So now we're given the names of the compounds, and we have to write out the formulas in order to balance. There's my copper by itself. Silver chloride. You have to know that silver's a +1, chlorine's a -1. You have to get the formula right so we get the numbers right. Copper, that Roman numeral 2 means that it's the copper that is +2. When we cross and drop, we get CuCl2, silver by itself. To balance it, 1 copper, 1 copper. I had 2 chlorines here, so I put a coefficient of 2 in front of this compound, gave me 2 chlorines. That also gave me 2 silvers, so I had to change this coefficient to 2 to make everything balance. The type of reaction here is single replacement because I had one compound and one of the elements was being replaced. You can see the silver was replaced in the compound with chlorine by copper. All right, so here we've got lead 2 carbonate. That's telling us lead is a +2, carbonate is a -2, and carbonate is the CO3. That's the formula for the carbonate ion. We're told here this is gold that has a +3 and hydroxide's a -1. So when we cross and drop, it has to be Au, which is symbol for gold, with a 3 down here because of the cross and drop. Cross and drop there gives us that formula for lead 2 hydroxide and gold 3 carbonate. Because gold is a +3, carbonate is -2. You can see the cross and drop comes out like that. Now, let's look at balancing. So here's my equation balance. You'll notice these numbers look a little sloppy because when you balance equations, you're going to have to just play around with the numbers. I picked one of the elements to start with, or one of the reactants or products started with, and then I started doing the math. I figured, oh, okay, I need a different set of numbers to make it balance. This will work. 3 leads, 3 leads. Think about the carbonate as one thing, and now I have 3 of that polyatomic ion, and over here I've got 3 of that polyatomic ion. 2 golds, 2 golds. 3 times 2, I've got 6 of these hydroxides. 3 times 2, I've got 6 over there. That's the coefficients that make it balance. I did forget to mention that this was a double replacement reaction. In the aluminum plus the iron 3 oxide. Iron's +3, oxygen's a -2. That's why I get Fe2O3. Aluminum's +3, oxygen -2, cross and drop. All right, so I've got 2 aluminums, 2 aluminums. 2 irons, 2 irons. 3 oxygens and 3 oxygens. And this here would be a single replacement reaction because I've got one compound that has one of the elements being replaced. You can see the aluminum replaced the iron with the oxygen. So here I've got copper and sulfur yielding copper 1 sulfide. +1, minus 2. That's why I get this formula. To make this balance, all I needed was coefficient of 2 in front of the copper, and it works. This would be a synthesis reaction because you're taking two elements and you're synthesizing a new compound. Now, you probably had a little misstep on this one, and that's this right here. Notice there's a subscript there, but there is no cross and drop. Understand why this 2 is there, because it came from the zinc. Where did this 2 come from? Well, this is chlorine by itself, and over here, this is bromine by itself. Remember that we have some elements when they are ever by themselves, they pair up with each other to help satisfy the octet rule, especially those group 17 elements. They are called diatomic molecules. And chlorine and bromine are both diatomic. So anytime they're written by themselves, they have to get this subscript down there, even though they're not being cross and dropped with another element. So this, once again, is an example of a single replacement, because you can see we had a compound and the chlorine replaced. There was one thing that was replaced in that compound. That's a single replacement reaction. All right, so here we got cadmium 2. That means its charge number is 2. Bromine's a cross and drop. Barium's a +2. Oxygen's a -2. So this is what we wind up with here. But this is already balanced. 1 cadmium, 1 cadmium. 2 bromines, 2 bromines. 1 barium, 1 barium. 1 oxygen, 1 oxygen. This is a double replacement because we have 2 compounds and they're both having something switched. So we got 2 or a double switch going on. All right, once again, hydrogen and chlorine, these are both those diatomic molecules. So they are always paired up with each other when they're by themselves. So we're going to run H2 plus Cl2 is going to yield HCl, hydrogen chloride. We need this coefficient of 2 to make it all balance. This would be considered a synthesis reaction because we have 2 single elements, and then we were synthesizing and we're making a new compound. And finally, here we go. We've got water changing into its parts of hydrogen and oxygen. This is the coefficients that will make it balance. This is a decomposition reaction where we're taking a compound and we're breaking it apart into its pieces. It's decomposing or breaking apart. So once again, if you have any questions about any of these, you can ask Ms. Campbell if you're in person, or you can email me. For those who don't know it, there's my email address. And at this time, you're going to assess what you know and how good you are with these balancing equations by taking the formative assessment that's posted on the Quizzes app. And the link will be listed there in Teams. It's going to be open, I guess, till tomorrow.